So I'll start once again with the potential energy of the particle executing simple harmonic motion. Taisir is here. Taisir? Or gone into hibernation mode. Was equilibrium position. X is equal to 0. Now you're going to apply a force. You're going to apply a force so that the spring undergoes an extension. The spring will undergo an extension X, right? You are applying a force. So this is force applied. There will be a restoring force acting in the opposite direction.
Ma'am, should we draw this as a diagram for this derivation?
No need, boys, no need.
Okay.
Diagram is not needed, only the statement is needed. So we started with this, the restoring force. The restoring force acting on the spring. So F is equal to minus Kx. We started with this. Did we start with this, boys?
Yes, ma'am.
Okay, fine.
Yes, ma'am.
Now, what we do is we want to find the work done in extending the spring. Suppose you in case if you, I'll come back to this. So the spring was here. Fine. Now you apply a force. So this will be force applied. Right? So that your spring extends from x is equal to 0. Say it undergoes a very small extension dx. You're applying a force. You're applying a force and doing a work is what?
I might have some connection issues at some point. So if I leave, it might be that because of that.
Okay. So what? You're applying a force, extending the spring to a certain distance against the restoring force. Right? Then we say a work is done by the applied force. Is that clear, boys? You're doing a work against the restoring force and then you are extending the spring by a distance dx. So let us find what is the work done by the applied force in extending the spring to a distance dx against the restoring force. So the next statement should be, the next statement should be work done, like work done by the applied force against the restoring force against the restoring force in extending the spring to a distance, in extending the spring to a distance dx to a distance dx. Now what will be this work? dw, so this is the work done against. Suppose if I write this as F applied into dx, but we very well know F applied will be opposite to, sorry, will be minus of F restoring, because both the forces are opposite in direction, boys. F applied is always acting opposite to the direction of the restoring force. So I can write dW is equal to minus F restoring into dx. But from equation 1, F restoring is equal to minus Kx. So I can write dW is equal to minus of minus Kx into dx. So dW becomes equal to Kx dx. This is the work done by the external force or the applied force in extending the spring to a smaller distance dx against the restoring force. The work done by the applied force against the restoring force in extending the spring to a distance dx. So dW is equal to Kx dx. Where is Jatin? Jatin? Jatin?
Yes, ma'am. Yeah.
Dheeraj? Dheeraj?
Yes, ma'am.
Boys, are you clear with this? If the applied force is always opposite to that of your restoring force. So this is the small work done in extending the spring through a smaller distance dx. Now next we have to find what is the total work done by the applied force in extending the spring through a distance x. Shall I go for the next one?
Yes, ma'am.
Next one. Work done in extending the spring to a distance dx, sorry, extending the spring to a distance x, to a distance x. This will be a total work. So W becomes equal to integral dW. So that is Kx dx. Now, where the limit goes, initially this, see, K is a constant, K is not going to vary, only X is a constant, X is extension, because X is the extension in the spring. Now, initially, what was the extension? X was equal to 0. Finally, the extension was X. So your limit goes from 0 to X. K is a constant. Your extension starts from a 0th value and it undergoes an extension of x. Now we have to use the identity x to the power of n dx will be equal to x to the power of n plus 1 by n plus 1. So x to the power of 1 integral x dx, I can write it as x to the power of 1 dx So that becomes x to the power of 1 plus 1 by 1 plus 1. So that is x squared by 2. Once this is your identity, x to the power of n dx is equal to x to the power of n plus 1 by n plus 1. Similarly, x to the x dx will be, because x has a power of 1, 1 plus 1 by, so it's x squared by 2. I can write this as k limit 0 to x, x squared by 2. So I'm applying the upper limit first. Boys, here the upper limit is x. So x takes the upper limit first, x squared by 2 minus your lower limit. 0 is your lower limit. So now x takes the value lower limit. So your work becomes equal to kx squared half kx squared. This is the work done by the applied force in extending the spring through a distance x against the restoring force. So whatever work has been done will be stored as the potential energy in the, whatever work has been done will be stored as the potential energy in the spring. So this work gives you the potential energy of the spring. This will be the work done in extending the spring through a distance x.
Ma'am,
Yes.
shouldn't work done be equal to kinetic energy? They change it kinetic energy.
No, this work done, whatever work you do in pulling the spring, now that work will be stored as the potential energy in the block or else in the spring. The moment you leave the applied force, all this work which is being stored as potential energy now will be converted to kinetic, so that now the spring will move in the opposite direction. So this is the work you do in extending the spring. So whatever work you are doing, because you have applied a force, you have moved the spring. So whatever work you are doing in extending the spring will be stored as the energy in the spring. The moment you remove your applied force, all this stored up energy will make the spring and the block to move in the opposite direction. It tries to come back to its original position. So potential now will be converted to kinetic.
Understood, ma'am.
Biological specimens are there in the class, boys. 11B has biological specimen, all hibernation, all
No, ma'am, we're all,
biology terms. Yes,
no, ma'am, we're all here.
what happened?
No, ma'am, no one
We're
is
all here, ma'am.
hibernating. We are all
That
here.
one
We're all
person.
here.
Oh, yeah. That one person only I'm talking about. One biological specimen in the class.
Maybe he might be busy hibernating now. He won't hear.
Yeah, ma'am. We don't know who that is.
Fine, fine. You carry on, boys. So
Ma'am,
W is
should we
equal
write
to
what
half.
you said?
Yes, yes, boys.
Should we write
Ma'am,
what you said, like
Yes,
the work
yes. You
done
need to.
stored as potential
Yes,
energy?
boys. Correct, correct, correct. Next slide. You complete this. So next slide, I'll write. This work done will be stored as a potential energy.
ma'am, if the recording was on, maybe we can get to know.
Okay, don't need boys. You just carry on. Will not waste your time. Just finish. Tomorrow I have to complete loaded spring. I think I don't know whether I'll have enough time to start with simple pendulum. Simple pendulum, loaded spring are the theoretical part. Then just a qualitative part, I have to go for resonance and damping. So most probably, if I can finish by tomorrow, it would be better so that I can start with waves next class. Have you completed?
Yes, ma'am.
Okay. So I'll go for the next one. Will someone take the snapshot and put it in chat box so that I can go for the next slide? Right, boys. Next one. This work done is stored as potential energy in the spring. So the potential energy becomes U is equal to half kx squared. Now we'll go for the total energy. The total energy of the spring. The total energy of the spring will be both kinetic and potential. So total energy is equal to your kinetic energy plus your potential energy. So kinetic energy, what was the expression for the kinetic energy we had? Half? Just the previous page.
Half m omega square
M
into
omega squared, a squared minus x
x
squared.
square.
Okay. Plus half kx squared. Correct, boss?
Yes, ma'am.
Yes, ma'am.
Now, I don't know whether, let me substitute for this m omega squared. I'm just redoing your restoring force. F is equal to minus kx. According to Newton's second law of motion, F is m into a minus k into x. Your acceleration is minus k upon m into x. So we just substitute, let omega square be equal to k upon m. It's angular frequency, k is spring constant. So a becomes equal to minus omega squared x. Okay, we'll check why k has, sorry, omega squared takes the.
Ma'am, but is it proven that omega square equals to k by m, or are we just
No,
assuming?
we are just, you're just assuming. Later on we'll prove. Once we move on to simple pendulum, let us see whether we can prove it over there or whether your syllabus is confined to prove. I don't know whether so many topics have been deleted. So right now you take it as omega squared is equal to k upon m. Sorry. So this is m omega squared. So I can write this as half k a squared minus x squared plus half kx squared. This will be your total energy. Now, can you find the final total energy? Can you expand the first term? Boys, can you expand the term which is now being highlighted? So that your final energy, total energy is half kx squared.
A square.
K a squared. So, okay. Are you getting this, boys?
Yeah, ma'am. Yeah.
Yes.
Yes, ma'am. We're getting that.
Okay. Now look at this. K is a constant. K depends on the nature of the spring as well as it also depends on other factors. So K is a constant. In an oscillation, if it is not a damped oscillation, which means there is no air resistance, any sort of resistance, then your amplitude, that is a maximum displacement, that also remains a constant, right? If there is no air friction, your pendulum keeps on oscillating with a constant amplitude. Then K depends upon the nature of the material. In case of a simple pendulum, your K also depends upon the mass of the spherical bob. So many other factors your K is going to depend on. So all those things are constant. Then I can say the total energy also remains a constant. That is what the second part of the question is asking you to prove, right? When the motion is simple harmonic in nature, prove that the total energy of the oscillator is a constant. This is how you need to prove. So the total energy remains a constant.
Ma'am, why did you
Yes.
write like A equals to minus omega square x, like on the right?
This one, right, boss? How is that we are arriving at it? Boss, right now you take it as an assumption, because let us see later on whether it is possible for us to prove. Might be in waves. Let us see whether it is possible to prove, because so many topics in between this academic year, your board has deleted certain topics.
All right, ma'am.
So that's the reason if I'm entering into that, it will be still an elaborate one. So right now you take it as omega squared as k upon m. If time permits, then because we need to finish whatever has been the revised portion. Once we finish, if time permits, let me see where I can go for this topic of proving that omega squared is equal to k by m.
All right, ma'am.
So we got an expression for the total energy. You have proved that the total energy remains a constant. Right? This was the second part of the question. Now comes the third part of the question. When the simple pendulum is oscillating, there are two positions. One is the mean position, the other one is the extreme position. So we have to check the energy at extreme position as well as what might be the nature of the total energy, whether it is kinetic or whether it is potential at the extreme as well as at mean position, right, boss? Right, boys. Graphical representation. This is very important graph. Graphical representation. So your total energy is equal to half k a squared minus x squared plus half kx squared, right? Sorry. Let me go only for kinetic and potential. So graphical at mean position. Mean means the rest position. At mean position, the value of x becomes equal to 0. I have a simple pendulum. This is your mean position. At mean position, your displacement is 0. So let us get an expression for your kinetic energy. Kinetic energy are k a squared minus x squared. So x is 0. Your kinetic energy becomes equal to half k a squared. So at mean position, your kinetic energy is half k a squared. Now what happens to your potential energy? The potential energy is equal to half kx squared. So when x is equal to 0, your potential energy becomes equal to 0. It means at mean position, your energy is purely kinetic. There is no potential energy. Is that clear, boys? At mean position, x is equal to 0. Your kinetic energy is half k a squared. Your potential energy is totally 0. Next, at extreme position, extreme, right, boys? This will be your extreme position. At extreme position, x becomes equal to a. So at extreme position, x becomes equal to a. So what happens to your kinetic energy? Kinetic energy, what is the formula, boys? Half k a squared minus x squared. So kinetic energy will be equal to half k into a squared x. X takes the value a. Kinetic energy will be 0 where at extreme position. Now what happens to your potential energy? It is half kx squared. X takes the value A, so potential energy will be half Ka squared. So at extreme position, x is equal to A, kinetic energy is 0, potential energy is half Ka squared. This is at extreme position. Complete this boys. Then we need to plot a graph. So at mean position and at extreme position. I'll put this in your chat box.
Ma'am, I did that already.
You have completed? Okay, fine.
But then also just give like 1 minute who like wants to.
Then I'll give.
No, ma'am. Siddharth told he put the screenshot in the chat box.
Okay, you take. Okay, no problem. You take your time. Finish this off, boys. I think it's mere substitution. People will under. Are you able to understand the concept, boys?
Yes, ma'am.
Yes, ma'am.
Boys, I'll finish the graph and then I'll. Just only one graph is required. To understand the graph, go home and learn. Boys, I'll just finish this off. Energy is along y-axis, displacement is along x-axis. I'll explain kinetic energy. You understand? You can put the same principle for your potential energy also. Right? So your displacement is equal to minus a at one end, 0 here. Right, boys? Now what if I put the energy, right? This energy is equal to half Ka squared. Now, what type of graph is this? Does this graph represent potential energy or kinetic energy? Let's look at this. At x is equal to 0, x is equal to 0 means what? Mean position. At mean position, look at the energy. Energy is maximum. So energy is maximum, so this becomes your kinetic energy. At extreme points, your energy is 0. At extreme points, the energy is 0. So this graph represents kinetic energy. I'll finish this off. The next one, at extreme points, the energy is maximum. This represents your potential energy. Fine. Those who have completed can leave. Complete your graph. Just try to do the, solve the graph, boys. Just go learn. Okay, fine. Learn the graph. You can leave, boys. Thank you, boys.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you.